first thing I should tell you is that we are recording this evening. We might use the footage on our website, it might go on YouTube, we don't know. We might send it to the Craft Council. We're also going to be taking photos as well. If you want more information about that, you can come and ask me in a break. So tonight is part of a nationwide programme called Makeshift Do, which is all about getting people, just normal people, involved and interested in making. So we're a makerspace. We are not for profit. We're run by hobbyists. We don't use this as a company. We don't make money off of it. We're just here all with a passion for making anything from the Dalek all the way through welding, soldering, 3D printing, to like sewing, baking, everything, any kind of making at all. There is some cake actually on the slide. So that's who we are. I hope you didn't have too much trouble finding us tonight. We're going to have just a series of talks tonight to kind of give you a flavour of some of the things that our members get up to. We've got Dave, who's going to start with something about oscilloscopes. We've got James, who is going to talk about ball balancing robots. We might have Benji on something. It was originally the Internet of Things. He may have changed his mind.
Budget smart home.
Budget smart home. So sort of home automation type things. And then we'll also do like a quick primer on like 3D printing as well, because we know a lot of people are interested in that, and we do have a suite of 4 3D printers here, which are available for our members to use as well.
And you've also got...
the wood workshop or the art?
Yeah, wood sports.
We've got Paul as well, so Paul's going to be talking about computers. So extra thing in there. I think that's it.
Right.
Would you like to take it away?
I will. So, as Jen said, I'm Dave. I've been an electronic engineer for forever, really my main interest in life. And up till recently I was paid to do it, but now I'm going to go make my own business and do it for real. So a lot of things are changing for me, but the core of it is really enabling building, making and doing it yourself. So DIY is a British thing, right? We've all done it. Everyone's granddad was always in their shed. They got to various reasons, hammering things to get away, or just because they like woodwork or making stuff. That's never ceased. So a lot of the people who come along here say, "Oh, I would really love to make a Dalek. I'd really love to make my own lighting thing, or make my phone do something cool with a robot, or whatever," but they don't know how to approach it. And they think the problem that electronics is complex. And electronics is complex. It can be complex, but it can also be very simple. So in recent history, things have kind of changed over to allow ordinary people, let's say, people without electronics degrees and whatnot, to play, to build things, to create things and to learn, and there's no pressure and it can be fun. So it doesn't have glory. Now, the problem with electronics, everybody goes on about the applications. I'm not picking any faults, but a ball balancing robot is fantastic and cool, but no one wants to talk about how you physically make things. There's very little around about the actual practicalities of what do I do with this thing? What do I do with this oscilloscope? How do I make it? What's available out there? So what I want to talk about really is not about oscilloscopes. I will talk about oscilloscopes, but that's just a thing. I want to talk about the practicalities of what all these little widgets are, and what you can buy, how you can combine them, and how you can start learning and making. So, probably one of the first things people will see is prototyping. Prototyping is the first thing that a professional engineer would do when they're making a product. So you don't start by making a final circuit board and an enclosure and whatnot. You lash your ideas out in some sort of temporary fashion. And one of the ways you can do that is to literally plug things into a prototyping board like this one. So I'll pass that around. You want to take a look at it. What it is a ready-made circuit board. So on that, there's an integrated circuit, there's an LCD, there's an LED, there's some basic electronic components, and you literally plug them in into something like a plug board. Now when you look at it, there's a bunch of holes in rows, in columns. All the holes in one column are connected together. So basically the columns of wires, horizontally in the rows, are separate wires. And that allows you to put a chip in the middle and connect a resistor to some of the pins on the chip to start building up the circuit. So you can see there, that's actually an Arduino compatible widget. So you could connect that to a USB programmer and plug it into a laptop, and you can make the LED blink, or in that instance start writing things to the LCD, the little organic LED display there. And you can start learning how the little bits of software and the little bit of hardware work together. But you don't have to make a circuit board, you don't have to solder anything. You can plug and play and take things out, put things in to get it all together. It's all very simple. So you can buy all these things from China. Here's a little Arduino programmer made by Master Jeremy over there. Donated a whole bunch of these. And you just plug it in with these wires into the appropriate pins on the chip, connect your USB on the other end, and you can talk to it. You can download software to it, you can whatever you like with it. It's very, very accessible. And at the other end of the thing, other end of the subject of prototyping and downloading and creating things, you can make it a bit more permanent. So this is it's a wireless 433 megahertz transmitter based on exactly the same thing. It's got the same chip on it, it's got the same basic components on it. I prototyped it on a breadboard like that, and then I made a circuit board, which we can do there. It's not that permanent yet, and it never actually got deployed into its environment. What that was, essentially, my wife wanted a clock that she could read at night. So, you know, to wake me up and ask me what the time was, which was a long cycle. So it's now in a massive picture frame with a huge display and a button. It's going to be radio controlled. That was the transmitter. I needed to make it work sooner, so I used to use a wire and we forgot about it. Anyway, so I got that as a good example of a circuit board which I created. Now the gubbins on the bottom are the wiring. It's just a layer of copper. The copper is selectively removed, so it starts with like this plate of copper. You selectively remove the copper to form the circuit. You drill the holes, you put the components through the holes, and you solder from the bottom. That's it. Very simple. Let me see if I can find some basic materials to show you what's available. Yeah, I had a bit of more copper here somewhere. There we go. It's around the other way. So that's kind of the other end of the prototyping. You've got the prototyping with the plug board, and then you've got the final thing, the circuit board. Be it a product, it could be a product, or in this case, it's just a basic one-off thing I made for a specific purpose. It all starts off as life as a bit of raw copper like that. And I'm going to show you how the process works, and we can do the process. You can do it tomorrow, but I won't be here tomorrow to do that. So halfway between that, there are other ways of doing things. So there are these nasty things, and I say they're nasty things, so I personally don't like them. But they're kind of like half a circuit board. And basically it's an array of holes. So the holes have the same standard spacing that most electronic components have. Most electronic components have a 0.1 inch pitch for the things you plug in, like the dipped chip, the 20-pin chip. So 0.1 inch, yes, thank you American. Yeah. Thank you Americans. Yes, everything electronics is imperial. It sounds crazy, right? But it is. So 0.1 inch pitch was the standard, and then it went to 0.05, and then 0.04, and they tried to go metric, but it ends up with a silly number. So really, everything is determined in mils, which is millionths of an inch. Imperial again. You live with it. It's tough. Anyway, so the thing I'm passing around there is basically a piece of circuit board that's got holes on a 0.1 inch pitch in X and Y, and it has there's some layers of copper. It's actually tinned copper on both sides, and you can use exactly the same thing. You can put the components through, but you just bend the leads around to make the circuit. There are no wires. There's nothing formed. You use the leads of the components, as I showed you around on there. There's resistors. You can see you have a couple of wires on them. You usually literally use those wires to form the circuit. This is why I say it's quite nasty, because it's actually really hard to do. Because with one finger you're holding the wire down, with the other hand you're holding the soldering iron, and where you're going to put the soldering, you need 3 hands. So what you end up doing is burning yourself a lot. So I don't like them. So for example, you know, an LED will come like that with its wires attached. Obviously when you put that on a real circuit board, you put it through the holes and then you cut the excess wire off and then all's good. But with these things, you literally would, excuse me, shove it through like that, bend it over, put the next component near it, sort of try and use those wires to make the circuit, and therefore you've got some sort of semi-permanent prototype. But it's not great. So I like making circuit boards. So how difficult is it to make a circuit board? It isn't. It isn't difficult at all. Don't get too hung over the actual complexity of the circuit. Everything can be broken down into basic components. A lot of people in the space here have a lot of experience with electronics and can advise on sort of patterns, things you can follow, cut and paste and join together. I never really start with a unique design. I'll just copy something else, delete the bits I don't want, chop something out I do want, and you know, you can come up with a basic circuit that I might want to show you here pretty quick. So when you want to go a little bit further, can we kill
More lights.
No, we can't kill more lights.
No.
Don't worry. Okay, it's a bit brighter than I was hoping in here. Anyway, so there's a kind of out of focus. I didn't check the focus.
On the top. On the top control panel.
Focus. There we go, that's got enough. So you can see the thing in the middle. That is that chip you saw, an 80 mega 328p made by Apple. So it's a nice chip. So people like me kind of get chips that they know inside out, that they always use because they just did it from them, and they're really cheap. You buy them in China for 20 for a few quid, and you plug them in and you know basically what you need to do. You need some basic components. You need a crystal, 2 capacitors, you need a couple of resistors and a couple of other parts off the edge of the screen, you can't see. And that's just enough to make that chip happy, and then you can start programming software on it, start prototyping, you can start playing. So now you've got your prototype on a plug board. You need to draw it as a schematic showing the actual connections between parts in a CAD package. This is DesignSpark, which is a free PCB design software from RS Components. Once you've done that, you can turn that into a layout. And it's so simple. Translate to PCB. So if I do that, I'll just do it live with the defaults. Oh man, yeah, okay.
This is DesignSpark, please.
This is DesignSpark, yeah. I wasn't really going to show this, but you know, I need to see, man, it's really good software. So when you put down a component, it has a symbol. This is a symbol. It's not really necessarily related to physically how the component looks. In the software, in the background, has an associated a footprint. Did you just crash? I think it just crashed. Oh dear. I can't show you that. So DesignSpark's got a new version that's a bit crashy, it turns out. So I've got an open case of them actually saying, your software's a bit crashy, what are you going to do about it? And they haven't got back to me. What it would have done is it would have said, okay, you've got all these physical components. I know you've got a capacitor, so I know it's the capacitor needs 2 holes, and it plonks the holes down with the correct spacing randomly somewhere on the board. And then you spend the next couple of days messing around, moving them around to make it as small as possible, and then you have the problem of just joining up the holes, effectively. So this is what I've done now. I'll show you the actual thing. I'll just remove that so you can see it better. Okay. So as you can see, that is the chip in the middle. That's just a connector, just a bunch of pins, not very exciting. There's a crystal, here's a capacitor, and it quite nicely shows you what the component is, roughly what's behind it, and you know those are the 2 litres of that capacitor, those are the 2 litres of that resistor, and so on. And you can grab them and you can spin them and rotate them in and around and generally make them, join up as you'd expect. Looking at the circuit, you know that, I know that when you design the crystal circuit, you must place 2 capacitors really close. It's just an electrical thing. Everybody who does circuit design knows about this particular thing. You just do it by default. So, following these sort of rules that you pick up over the years, or basically you just ask someone how do I design a crystal oscillator circuit, they'll show you. You plonk it in, and it'll be fine. And then you just join it up. Now, what you would have started with, if I hadn't actually shown you the final board, would look a little bit like that. Got a rat's nest. So what it's basically saying is, I know where those 2 components are, but you haven't joined them up yet. There's no copper, there's no connection, there's no wire, there's no nothing. So it's telling you that you want to join those up. And the tool will help you. It'll remind you, if you haven't wired that up, it'll say, oh, you've shorted those 2 things together, you need to do that. And all these sort of things. It won't generate a correct board, it won't let you produce something which won't work. So the process of design is really just to draw the wires that you want in the shapes you want, to join the components to form the circuit that you want. Like this, for example, I could just join that like that. And it's just like drawing, really. And away you go. It takes a little bit of skill, but it's not difficult to learn. It's just a matter of drawing, effectively. So when you've done all that, you can produce masks. And you just print it out. So I just print it out. I'll pass some of these around. Here's some things I designed last week.
You're skimming lightly over the fact
I am skimming very lightly over something that's got a history of 100 years yet.
Wires.
Yes. So, one of the limitations that's very hard with electronics when you're DIYing it is the number of layers on the circuit board. As you saw with this little guy, there's only 1 layer, which means you can't cross wires. If you cross them, they're joining because they're the same piece of copper conducts your stuff. So what you have to do is do horrible things like put jumper wires on the other side and then solder them and nasty things like that. In reality, as you're alluding to, is you'd have more than 1 layer. In fact, to be practical, you'd have 2 layers, 1 on each side. That way, you could have all of your horizontal wires going that way on that surface, and all your vertical wires going that way on that surface. You could therefore cross wires because they're not physically the same piece of copper, because they're separated by a nice insulator. And then if you wanted to join them, you drill a hole, you solder both sides, and everything's happy. Anyway, so double-sided is a bit harder to do here, and I've never actually personally attempted it in this space. But I'm going to. So, here's a more complicated design. Now, this is what you allude to. This is the most complicated single-sided design I've ever achieved. It took me 2 weeks, and I'm never doing it again. This was actually for the product you see over here is an infrared reflow in my building, and we needed a controller. So we prototyped the controller on a plug board, literally plugging it in, controlling a mains device. We know it all works, so someone said we need a PCB, just like a board, to make it real, to make it such that you can pick it up off the shelf and put it down, it doesn't break. So that is the layout for it. So what does it look like? I'll show you because I've made it the other day. So the 2 masks I showed you around are for basically a very simple photographic process using ultraviolet light as the results. So as you can see, you compare them with the mask. If you get the mask and the physical board together, you can have a look and see how close they are. But effectively what you do is you take some copper board like that has a ultraviolet sensitive layer on it. You peel the black plastic covering off, you stick the mask on it, you put it in an ultraviolet light box, like that one, you irradiate it for about 4 minutes flat, and you throw it in some chemicals. And the chemicals will dissolve the areas that were exposed to light, leaving the areas under the mask as a protective layer of the copper. You then put it in an etchant solution, and it dissolves all those bits of copper you don't want and forms your traces, exactly as you see wherever it went. It's not copper coloured because it's got the polymer still on top of it.
What did you put in your printer? You have a transparent.
That is 90 grams per square metre tracing paper,
Right.
which is quite expensive. It's about £7 for 20 sheets, but I find it gives you... The problem is that a laser printer uses toner. The toner sticks to paper very well because the paper has a grain, a microstructure to it. But paper isn't UV transparent enough. It means you have to expose for hours on end. So people start to use overhead transparency films and they put them through a laser printer. So when you get plastic and you melt it onto plastic, it just makes a mess. You end up with smeary tracks. You end up with black that isn't black enough. So you end up then taking multiple layers and stacking them on top of each other. Now you've got an alignment problem and it is horrible. Tracing paper is really lovely because it's transparent enough, but it still has that lovely grain structure to the toner soaks into it and it ends up with black and blacks, which means you only have to go with one layer, which means you can achieve more accuracy. And if you look at the PCB that's going around, I'm quite pleased with that, I have to say. I'm quite smug about it. It's, you know, basically using a home 60 quid laser printer, a bit of tracing paper, an ultraviolet light box that's 30 plus years that was in someone's granddad's shed, which has got a really dodgy tube in it, but it works fine. And it produced a circuit which is actually pretty good. As you can see, it has no holes in it. I need to drill them. There's actually a drilling press up there, but I'm going to build a better one. So eventually that will have a mixture of surface mounted components and through hole components. All the components that are on that plug board that I showed you and on here are through hole because the leads go through a hole. So electronics isn't complicated, it's quite simple really. The most real things like mobile phones and what have you, they have a mixture. In fact, they're predominantly surface mounted, a bit like the Raspberry Pi. So you'll see that there aren't too many holes on there. If you look at the bottom, you can't see too many components that have leads on them that go through a hole, because that's 30 plus years old technology. It's not very useful anymore. It's very hard to make things small. So you shrink things down by making the components sit on the surface. But that causes other manufacturing problems, and it's quite hard to do DIY. So the little circuit that, with a more complicated circuit, is dominantly surface mount. It's a little bit more of an advanced manufacturing technique and allows you to stuff more onto a smaller board. It also allows us to use our infrared reflow oven to make it self. So there's a little bit of a joke in that 3D printers make themselves. So all the parts in this 3D printer are 3D printed. So obviously you've got chicken and egg problem. But the problem is that 3D printers have been around for ages, right? So the company that makes these has a big long line of 3D printers making parts for more 3D printers, and it's just a bit of an in-joke that it makes itself. We're doing the same thing with this circuit board. So we're going to use the prototype on the breadboard to drive the oven to solder the PCB that it's its own controller. So the next time it runs, it will have the real circuit in it, which reflowed itself with the same software, with the same chip, just because we can. We haven't got that far yet. I need to get a better job. Anyway, so that's a bit about PCBs and software. PCBs and embedded software and manufacturing techniques. The subject is huge, and realistically what you can achieve in a makerspace is limited. In reality, things like the Raspberry Pi have 4 metal layers, and that's going to cost you a few £1,000s per prototype, and it's going to take a few weeks. So every time you make a design pop-up, a big change, which happens a lot, you have to chuck all your boards away, modify it, make new masks, send them out to manufacture, wait 2 weeks, give them several £1,000s, pray, it comes back, you then solder it, build it, test it. Oops, I made another mistake, and around you go. That's expensive. In a makerspace, you can just make a PCB and in a few hours, test your prototype, cut a few tracks with a knife, make a few solid bridges, bodge it, you're done. And if you want to make a pretty one, you can just do it again. And that's what I like, it's rapid prototyping in-house, just making stuff until it's good enough. It doesn't have to be production quality, it just has to be good enough to solve the problem you want to do. Because invariably you're making one of something. A custom thing for your car, or just a toy that you got bored of because you've gone to the next idea, and you know. So, I'm going to move away from PCBs and software and prototypes and a few more minutes on what I actually said I was originally going to talk about, which is some of the tools of the trade. So, I guess most people have come across the ubiquitous multimeter. This is my little one. I don't know quite why they need to be so big. I mean, I had one about that big when I was 15, but for some reason they need to be massive and have a massive screen on them.
They're easier to find.
I don't know. I mean, that box is pretty big, but it takes a load of space in it. I could have a little dinky one. I mean, you can get the Delta watches, can't you, if you ever finish it? Anyway, so this measures basic things. It'll take a measurement of voltage, of the current flowing through something. You can measure the resistance of a resistor because you can't bother to read the little codes on the side. And you can use it to look at short circuits and things like that. It's a basic debugging, general engineering tool. Most people probably got one, most people probably don't know how to work it.
Do you get bigger ones because you bad eyesight?
I think they make them big because a lot of people have bad eyesight. I can actually read things that small and not beneath digits that big. I don't know why it needs to be like that. You can get talking ones too. Yeah, that one even talks to the computer for some reason. But you're going to be limited. So a multimeter is going to allow you to measure, debug, and basically play with things that are static. So what's the voltage on this thing? Is this battery flat? Is it a 9-volt battery? Stick 2 probes on it. If it reads 7 volts, chuck it in the bin. If it reads 9 volts, plug it in your 8 volt, whatever. Well, basic stuff. But electronics isn't about static things, it's about signals. It's about change, it's about adapting and controlling. So, what if you, for example, have a really bad, noisy stereo system like the one over there, which is about 25 years old, and you want to know, where's the noise coming from? What does it look like? How can you see the noise? You can't. You can't see noise. You can just hear noise. How are you going to trace it? The multimeter is going to tell you a few things like what the voltages are, but it's not going to give you many more clues, especially if you don't really know how exactly that circuit works, which is what you use an oscilloscope for. So this is a fairly high-end one. You just attach a signal to it and show you roughly why it's so damn useful. There's the idiot button. I didn't press that. Anybody who knows about electronics, I've just committed a cardinal sin in an oscilloscope by pushing the auto set button. Oh yeah, right there. For those who can't really see the screen, it's a bit tiddy. I'm going to attempt something I've never tried before, which is to connect a projector to an oscilloscope. But unfortunately it's running Windows 95, so who knows what's going to happen. Let's give it a go. Amaze me. How about that? It's worked. Blimey. Right, so back in the old days and in school, and when you do oscilloscopes in school, you'll have some horrific little, they're awful. My wife was a science teacher, and she brought this thing back and she showed me how to work it. I was like, I don't want to touch it. I don't want to touch this awful ancient bit of history. It had a green screen, yes, it had clicky dials like this guy here. So this is your very basic sort of cheapo oscilloscope. It's powered up. And it has all the features, don't get me wrong. If you have chosen this and nothing, I'll take this any day. But if you want one of those, whatever. And there's the same boring signal. This is a calibrate signal, don't worry about that too much. All scopes have this feature. It basically allows you to adjust things. So what you're showing now is a square wave, which is what's a square wave. So basically there are two voltages going on here, the off voltage and the on voltage, or the low voltage and the high voltage. So now you've got some more information about the thing you plug it into. You now know its range. How low does the signal go and how high does it go? You also know that it's a pretty boring signal. It might be a wobbly. If the bottom was wobbly but the top wasn't wobbly, that actually tells you something. It tells you about your pathway. So all these things you can learn immediately. Put an oscilloscope on a signal and go, aha! Little light bulb goes off and you go away and look at a different bit of the circuit. You find a bad joint, you find a duct capacitor, replace it, and you're done. Easy peasy. So what can we tell about this signal? We know its range. So there are many technical terms in electronics. One of them in particular is peak-to-peak voltage, the low peak to the high peak. So an oscilloscope will let you measure that. So you can see, if I just adjust the vertical position so the bottom lines up with the centre here, you can see it's 2 1/2 of these graduations from the bottom to the top. And I also know that the meter is set to lowest in range with a little arrow, 0.2. So I know that each of these little divisions is 0.2 volts. So that signal is 0.2 plus 0.2 plus half, 0.5. So it's half a volt. peak to peak, bottom to top. So I've already learned something. I also know that, no, that didn't work, never mind. I should learn how to work this calculator, shouldn't I? I know how to work that one. You also notice there's something happening in the time domain. So what the oscilloscope is really doing is it's starting here, it's showing you how much voltage there is over time. So time is going this way, voltage is going that way. And we can adjust the horizontal scale by making it scan faster. So his is going really slowly, but it's kind of hard to work out what shape the signal is. And if I go too fast, you still can't see the signal. You've got to go just slow enough to get some more information. So we can measure how long it takes a signal to repeat, which is frequency. The mains frequency is a sinusoid which changes 50 times a second. That's our standard in this country, and it's 60 times a second in the US. So from here to here I can measure, just zoom out with it, it's about 2 divisions. So it goes low for one, high for one, and then low for one, and high for one, and repeat. So horizontally, it is set to 0.5 milliseconds per division. So it is 1 millisecond period, because the signal repeats every millisecond, i.e. 1,000 times a second. So that's a 1 kilohertz square wave for 0.5 voltage, 0.5 volts peak voltage. And we're already talking electronics. So that's useful information. Anyway, we won't look at that anymore, that's boring. So basically your oscilloscope is a window into a circuit. What is it doing over time? How is it varying? Is there noise? Does it look weird? How high, how low does it go? If it repeats, how does it repeat? And exactly the same thing on here, but this scope's pretty cool. There's all sorts of neat gadgets. Because that was too much effort. So we're quite lazy as electronic engineers and we try to get the tools to do everything for us. So this one has a computer in it. And I can do some neat things like push that button there, measure frequency. I want to know peak to peak voltage. There you go, that's easy. I can just read it all out for you. You can see here the period of this particular signal is 1.4 milliseconds. I don't know why. The calibrate signal is slightly different on this scope, and it's 1 volt from there to there. Easy peasy. So basically that is all there is to the oscilloscopes. From them, you're basically debugging, and from a very simplistic point of view, you can graph a signal, you can analyse a signal, and you can print it out and say, hey, what the hell's going on here? Someone knows what I'm talking about. So we can do that here. We've got this guy, and he's very useful if you know how to work him. I've probably well overrun these kind of subjects, so the thing with electronics is the more you talk about it, you think, oh no, I've forgotten about this and that, and there's so much to it. There's power supplies which you can tweak the voltage with, so you can just power something up real quick on the bench and not have to go get a battery or a power supply circuit or whatever. You get your lab power supply, stick it on the bench, crank the voltage to 7.5 volts. Set the current limit to something low, so when you make a short circuit, it doesn't burst and flames. Very useful feature. And we literally have created fire using a bench power supply. Everybody who's ever been in a physics high school class has done exactly the same thing. Right? With me, it was magnesium ribbon, then they banned that, and very boring. But anyway, so we have some basic electronic equipment. We're always on the lookout for anything more that is useful. Function generators, frequency counters, all those sorts of things add to sort of general tool set that we can call upon to analyse a problem, to drive a prototype, to basically just tinker around with stuff we build. Okay, I'm going to leave it there. I might talk a bit later if anybody wants to ask any specific questions like how does XYZ work, or explain this, I can do so. That's kind of my very ranty ad-lib, totally unprepared presentation.
Thanks, Dave. So basically the theme of tonight, hopefully you may have caught on, is that you just can. You don't have to have all the knowledge, you don't have to be a professional. You can just come down, well, you're an engineer to an extent. You can just come down and see what people are doing, ask them questions, say, I really want to make this thing. And then, someone here is going to take an interest and help you. 18 months ago, someone went, I want to do a garlic. We now have a garlic. We can. That's kind of the whole point, really. So I think we're going to move on to James.
Yeah, okay.